In this video we're going to create a dynamic model of a MOSFET by finding the parasitic capacitances in a MOS device. Looking at a MOSFET cross-section should make a few capacitors jump out at us. Pause the video and write down a few capacitances, 2 or 3, that you see in this device cross-section. The first quick ones are the junction capacitances between the drain source and the body. These are sometimes called diffusion capacitances in MOSFETs because the drain and source layers were created by diffusing material into the substrate in older MOS processes. The second really important capacitor is one that we put in place on purpose, the gate-to-channel capacitances. This capacitor is how we created the electric field that makes the FET part of a transistor. We've calculated the gate capacitance previously when we were trying to figure out how much charge was in the channel to find our IV relationship, and that calculation is down here. The gate-to-channel capacitance is given by the Cox times WL, where Cox is the gate-to-channel capacitance density, W is the width of the MOSFET, and L is the length of the MOSFET. This capacitor is a little bit weird for our circuit modeling because it doesn't connect to our device terminals, like the drain or the source, but we'll tackle that on the next slide. Finally, there's a sneaky capacitance that you may not have been able to see in the big drawing, but the gate overlaps the drain and the source by a tiny amount. This happens because of a fabrication technique called self-aligned source-drain implantation, which uses the gate itself as a screen to prevent dopants from getting into the channel. These small capacitances are called extrinsic drain and source capacitances, and they're named CGDO for gate-drain overlap capacitance, or CGSO for gate-source overlap capacitance. Okay, we need to figure out how to model this gate-to-channel capacitance that we have here. And we don't want to add a channel node to our small signal model. So we need to assign this capacitance to our device terminals. We do that in different ways in the linear region and the saturation region. In linear, the channel is low impedance and it connects both the drain and the source. So we just split the gate capacitance in half between the drain and the source, as shown in the equations in the lower left here. We say that the total gate source capacitance is the extrinsic CGSO plus the intrinsic capacitance 1/2 Cox W times L, and CGD is similar. In saturation, the channel doesn't go all the way from the drain to the source because it's pinched off here. So we assign all of the channel capacitance to the source. Also, cutoff means the total size of the channel is a bit smaller, so we're going to assign some reduced fraction of the channel charge to the source instead of the full Cox times W times L. That fraction turns out to be 2/3 for old school transistors, though that fraction varies in modern devices. The only capacitance assigned to the drain in saturation is the extrinsic overlap capacitance. We can combine all of these capacitors to make a small signal model for the saturation region, and that's shown over here. The gate-to-drain capacitor has been connected between the gate and the drain. The gate-to-source capacitor has been connected between the gate and the source. One feature of note is that FT for MOSFETs is exactly GM over CGS plus CGD, because our input is purely capacitive. There's no RPi in the way to make it a tricky first-order system at the input. It just looks like an integrator. And we indicate that because the approximation we used in our earlier FT equation has been replaced by inequality here. Also, note this is the equation for radians per second and not hertz, so that's a little bit of a misnotation. However, we've also forgotten terminal in our quick small signal model. Don't forget that we still have junction capacitances to our body down here. So in summary, most MOSFET capacitance deliberately comes from the gate-to-channel overlap. That gate-to-channel cap gets split between the drain and the source, half to each side in triode, or 2/3 all to the source in cutoff. And additional parasitic overlap caps exist that connect the gate to the drain and to the source. So finally, that gives us a small signal model down here, summarized by these equations.